Welcome, curious minds, to the deep dive. Today, we're taking a closer look at solar technology. Specifically, we're shining a light on how companies are constantly innovating, trying to make solar panels more efficient and, stronger too. Our guide for this is actually a pretty interesting document, a U.S. patent. It's number US 2666732B2. It was granted to a company called JA Solar Technology just this past April 1st, 2025. And look, this isn't just some dry legal thing, it's really a peek into the future of renewable energy.
That's absolutely right. Think of it less like a legal document and more like a blueprint, a really detailed one. It's for, well, the next step in solar energy production. And it comes straight from the inventors at JA Solar Technology Yangzi Co., Ltd., over in Jiangsu, China. The names listed are Hongyi Chen, Jianjun Li, Yanfeng Zeng, Xiaosu Kan, and Xiaowei Sun. Quite a team.
Okay, so what's our mission today? We want to sort of introduce you to JA Solar, using this patent as our lens. Then we'll explore the kind of innovation they're bringing, get into the problems they're trying to solve, and then really dig into the specific, clever solutions they've outlined in this patent. Okay, let's unpack this. So to really appreciate what's going on in this patent, we probably need a bit of context on JA Solar first. Now, the patent itself, it doesn't give a full company history, obviously, but it does drop some important clues about their strategy, right? It mentions their continuous development of a manufacturing ability of crystalline silicon and also their ongoing research on high-efficiency solar cells. What does that tell you, especially that focus on manufacturing ability?
Yeah, that phrase manufacturing ability, that's really telling, I think. In this industry, lots of companies focus purely on designing the next best cell, which is important, of course. But JA Solar saying this signals something deeper, a commitment to the process, how to actually make these advanced cells efficiently, reliably, and crucially at scale.
Ah, okay. So it's not just the invention, it's the production line too.
Exactly. It suggests they're thinking about controlling quality and cost right from the raw silicon stage all the way to the finished panel.
Yeah.
That's a huge advantage in a market this competitive. It's about being a master producer.
Right. Mastering the how, not just the what. And the patent also mentions their progress in high-efficiency multi-bus bar solar cells.
Mhm.
Okay, for listeners maybe familiar with solar basics, but not, the nitty-gritty like bus bars.
Yeah.
Why are multi-bus bar cells such a big deal? Why is that a focus?
Good question. So traditionally, you'd have maybe two or three fairly thick metal lines, the bus bars, on a cell's surface. Think of them like, I don't know, main highways carrying the electricity away.
Okay.
But those thick lines, well, they cast shadows. They block sunlight from hitting the active silicon underneath.
Right, less light means less power.
Precisely. Multi-bus bar designs flip that. They use many more lines, maybe 9, 12, even 16. But this is the key. They make them incredibly thin, like tiny wires instead of highways.
Ah, okay. So more paths, but smaller paths.
Exactly. This network reduces electrical resistance, so less energy is lost as heat, more power gets out. Plus, it actually makes the cells tougher, more resistant to tiny cracks.
Oh, interesting. Didn't expect that.
Yeah, it's a nice side benefit. So they're more efficient and more robust. That's why, as the patent says, their market share is getting higher and higher.
Yeah.
JA Solar focusing here shows they're right at the forefront of what's commercially viable and really effective solar tech.
Okay, so even just from this patent, filed back in Feb 2023, granted recently, we get a picture of JA Solar as a company that's really pushing things forward, pushing on both the cell design and how to actually manufacture it effectively. It's not just theory.
Definitely. It's a tangible piece of evidence of their ongoing R&D and market strategy.
All right, now let's get into the challenges. To really appreciate JA Solar's solution, we need to understand the problems they were tackling. So, when someone looks at a solar panel, maybe on a roof, it looks pretty simple, right? Flat piece of glass. But you're saying the engineering underneath, especially on the back, is actually quite complex. What are the hidden headaches?
Oh, absolutely. It looks simple from afar, but up close, it's a complex sandwich of materials, especially on the back surface. That's where all the electrical connections happen, where the power actually leaves the cell string. Every single layer, every connection, it has to be optimized for light capture, for power transfer, and crucially, for lasting maybe 25, 30 years out in the weather.
Right. It's a tough environment.
It is. So it's this constant balancing act between different materials and physics.
Okay, so let's talk specifics from the patent. It highlights problems with the encapsulant material layers. Those are the clear protective layers, right? Shielding the cells.
Exactly. They seal everything up, protect the delicate silicon cells from moisture, dirt, impacts, you name it. Essential stuff.
But the patent says if they're too thick, that's actually a problem for efficiency. How does that work? What's the trade-off?
Well, think of it like putting layers of cling film over a camera lens. Each layer is mostly clear, but add enough layers, and things start to get hazy.
Okay, yeah.
It's similar here. These encapsulant layers, even though they're designed to be transparent, they aren't perfectly transparent. If they're too thick, and traditionally they could be, say, zero point 0.5 millimeters or even more, they inevitably absorb or reflect a small amount of the incoming sunlight.
Ah, so less light actually reaches the silicon underneath.
Precisely. Every photon lost is potential power generation just, well, gone. So engineers are always fighting to make these layers as thin as possible without compromising protection.
It's that balancing act again. You need the shield, but the shield itself can get in the way. What about those welding strips, the little ribbons connecting the cells? What problems do they cause?
Right, the welding strips. Another critical component, but also another source of engineering headaches. They're vital for collecting the electricity from the cells. But like the old bus bars, they physically sit on the cell surface.
Meaning they block light too, shading.
Exactly, they create shading. It might seem small, just tiny ribbons, but add up all those ribbons across a whole panel, and it's a noticeable loss of active surface area. This directly impacts something called the fill factor, which is basically, a measure of how effectively the cell's area is actually generating power. Lower fill factor equals less power from the same size panel.
So they block light, reducing efficiency. The patent also mentions something about them being stiff, traditional ones anyway, even at 0.2 millimeters diameter. Why is stiffness a problem?
The stiffness issue. That relates to reliability in manufacturing. Solar panels aren't perfectly rigid structures. They flex slightly during transport installation.
And just day-to-day temperature changes, right? Expansion, contraction.
Absolutely. Big temperature swings. If those tiny welding strips connecting the cells are too stiff, they can't easily accommodate that movement. Over time, this stress can lead to microcracks in the cell or the connections breaking down. Delamination.
Which sounds bad, leading to performance loss or failure.
Both. It can create hot spots, reduce output, or in worst cases, cause parts of the module or the whole thing to fail prematurely. People try different things like segmented strips or triangular ones, but the patent suggests those have their own issues, harder to manufacture, maybe still impacting the fill factor negatively.
Okay, so we've got these encapsulant layers potentially being too thick, blocking light, and welding strips that also block light and can be prone to physical failure if they're too stiff. Quite a challenge. So how did JA Solar tackle this? What's the core innovation in this patent, US 122666732B2?
Well, this is where it gets pretty clever. They didn't necessarily invent a brand new miracle material. Instead, they focused on let's call it a refined manufacturing method, a new way to structure the layers. It's about the arrangement and application of these materials, particularly around those welding strips. It's subtle, but really smart.
A refined method, like a microscopic choreography you said earlier. Okay, let's break that down. You've got the main solar cell string, and on the back, those welding strips carrying the current. What's the new sequence JA Solar came up with?
Right, it's about being very precise and localized. Here's the sequence they describe. First, they put a first layer of encapsulant material directly onto the back of the welding strip itself.
Okay, so right on the strip.
Yes. Then they put a second layer of encapsulant, but this one goes onto the back surface of the solar cell string, only in the area right where those welding strips are located.
Ah, so not a full sheet covering everything, just targeted strips of encapsulation.
Exactly. It's localized. It's not one single thick layer smeared across the entire back anymore. And then finally, they laminate the whole thing together. The cell string, the strips with their encapsulant layers, the back sheet, everything to form the complete module.
Okay, I think I get it. Instead of one thick protective blanket over everything, it's like targeted layered protection specifically around the sensitive welding strips. What's the big advantage of doing it that way? Especially thinking about that thickness problem we discussed.
The advantage is huge. Because they're applying it locally and in these distinct layers, they can make each layer incredibly thin. The patent actually specifies that each of these encapsulant layers can be less than 0.1 millimeters thick.
Less than 0.1 millimeters.
Each.
Yes.
Resulting in a total combined thickness for the encapsulation around the strip of less than 0.3 millimeters.
Wow. Okay, compared to the 0.5 millimeters or more you mentioned for conventional methods, that's a massive reduction, almost half or even less.
It's a significant improvement. And that reduction in thickness directly translates to less light being absorbed or reflected by the encapsulant itself.
So more light gets through to the silicon. Higher efficiency.
Exactly. Better light transmission. But that's not the only benefit.
Right. You mentioned protection for the strips too. How does this thinner layered approach help with the stiffness and potential cracking issues?
Because the welding strip is now essentially cocooned between these specifically applied encapsulant layers. It provides full protection, better cushioning against mechanical stress, and better adhesion. This makes the whole connection much more reliable, much less prone to those micro cracks or failures caused by flexing and temperature changes over the panel's lifetime.
Makes sense. And they didn't stop there, did they? They also refined the welding strip itself.
That's right. The patent mentions they can now use a thinner, circular welding strip down to just 0.125 millimeters in diameter.
Okay, 0.125 millimeter compared to the zero point 0.2 millimeter example earlier. That's what, nearly 40% thinner?
Yeah, about a 37.5% reduction in diameter. And because it's thinner, it casts less of a shadow.
Less shading again, more active cell area exposed to light.
Precisely. So you get a boost from the thinner encapsulant, letting more light through, and another boost from the thinner welding strip, blocking less light. It all adds up.
And wasn't there something about a high reflection backplate too?
Yes, they mentioned that as well, using a backplate material that's highly reflective. The idea there is that any light managing to pass through the silicon layer without being absorbed gets bounced back up by this reflective backplate.
Giving it a second chance to be absorbed by the silicon.
Exactly. It's like getting a second bite at the apple for those photons. It's another way to squeeze out just a little bit more efficiency.
So it really is a combination of things. Thinner protection, less shading from connections, better reliability, and even recycling photons from the back.
It's a holistic approach, improving overall module efficiency, increasing stability, reducing the amount of material needed, which could also impact cost, and improving the bonding between all the layers.
Okay, so let's zoom out. What does all this mean for you, the listener, and maybe for the bigger picture of solar energy? We've dug into just this one patent, US 12266732B2 from JA Solar, but it feels like it tells a story about this quiet, continuous improvement happening behind the scenes.
I think that's exactly right. This deep dive really highlights how these incremental but really quite significant innovations in materials and, importantly, in manufacturing methods are critical, making solar cells more efficient step by step, making them more durable, maybe using less materials so they become more cost-effective. It's this kind of clever design work by companies like JA Solar that genuinely pushes the boundaries and makes solar power more practical, more reliable, more deployable.
Yeah, it's easy to forget that huge technological shifts are often built on lots of these smaller, detailed improvements, like tweaking the thickness of a layer by fractions of a millimeter or redesigning a tiny metal strip. But it adds up. It really shows how these details impact the performance and ultimately the viability of the technology that's meant to power our world.
And that brings up maybe a final thought for you to consider. Think about how these ongoing, very detailed advancements that kind of often hid away in complex patent documents like this one, how they might compound over time. How could these continuous improvements in efficiency, durability, and cost ultimately reshape things like global energy independence or environmental sustainability in the coming decades? It's not one giant leap, but maybe thousands of small steps adding up.
A powerful thought. Thank you for joining us on this deep dive into solar innovation. Until next time, keep learning, keep questioning, and keep exploring.